Hi, today I will be presenting my assignment for computational mathematics and statistics. My presentation consists of two main parts. The first part focuses on numerical method, while the second part focuses on the statistical analysis. This presentation is divided into two sections. In part 1, I will discuss two numerical method questions. The first question involves solving a system of complex linear equations using the Gauss-Seidel iterative method. The second question compare the force position method and the Newton-Raphson method for finding the root of the nonlinear equation. In part 2, I will analyze examination results for three professors using statistical techniques such as distribution analysis, standardization, ANOVA, and Levin tests. Finally, I will explain the proposed grading scheme based on the Z-score. I will first present the numerical method section. This section consists of two questions. The first question applies an iterative technique to solve simultaneous equations with complex numbers, while the second question compares two different root finding methods and evaluates their efficiency. For first question, we are given a system of two simultaneous equations containing complex coefficients. To solve this problem, I first express each complex variable in terms of its real and imaginary components. Specifically, I wrote Z1 as S1 plus Y1i and Z2 as S2 plus Y2i. Next, I expand to both equations and separate the real and imaginary parts. This converts the original complex system into four real linear equations involving the four unknowns x1, y1, x2, and y2. Instead of solving this equation directly, I rearrange each equation into the Gauss-Seidel iterative form. The Gauss-Seidel method updates one variable at a time using the latest variable values from the current iterative. The initial value for all four variables was set to 0, and the iterative process was then carried out repeatedly until the value remained unchanged at 5 decimal places after convergence. The final solution obtained was x1 equal to y1 equal -3, y x2 equal 1, y2 equal 4. Therefore, z1 equal to 2 minus 3i, z2 equal to 1 plus 4i. These are the final solution of the original complex solution. This slide shows the iteration result generated in Microsoft Excel. The first row represents the initial guess, where all variables are set to 0. As the iterations continue, we can observe that the value gradually moves closer to the final solution. During the early iterations, the changes are relatively large because the estimates are still far from the correct answer. However, after more iterations, the differences between successive values become much smaller, indicating that the solution is converging. By, alpha- by approximately the by approximately the 75 iteration, the values remain essentially unchanged at 5 decimal places, showing that the has been achieved. The final value are x1 equal to y1 equal -3, x2 equal 1, y2 equal 4. This confirms that the Gauss-Seidel method successfully solved the system of equations. The Excel implementation also demonstrates how iterative numerical methods are gradually approach the exact solution rather than obtaining it in a single solution. Next, I will discuss question 2. The objective is to determine the intersection point between the two functions g of s equal s to the power of 6 and h of s equal to s plus 1. To solve this problem, I first rewrote it as a root finding problem by defining a new function, f of s equal s to the power of 6 minus s minus 1. The root of this equation corresponds to the intersection point of the original two functions. The given interval is from 1 to 1.5. Before applying the force position method, I evaluate the function at both endpoints. Since the function value have opposite sign, this confirms that a root exists within the interval. The force position method estimates the root by drawing a straight line between the two endpoints and calculating where that line intersects the horizontal axis. After each iteration, one endpoint is replaced depending on the sign of the new function value, while the other endpoint remains unchanged. This process gradually narrows the interval containing the root. The Excel table shows that the estimate roots move progressively closer to the actual solution. After adding iterations, the method converges to 1.13 472 with a true error 0.00037%. Although the method is reliable because it always keeps the root inside the interval, its conversion becomes lower near the end because one boundary remains fixed and many iterations. Therefore, while the false position methods provide an accurate result, it requires considerable more iterations than some other numerical methods. Now I will introduce the second method used to solve the same question, which is the Newton-Raphson method. Unlike the false position method, the Newton-Raphson method uses both the function and its derivative to estimate the next approximation. In this case, the function is f of x equals x to the power of 6 minus x minus 1, and its derivative is 6 x to the power of 5 minus 1. The initial guess was chosen as x equals 1 for each iteration. The current estimate was substituted into the Newton-Raphson method to obtain the next approximation. From the Excel result, we can see that the solution converges very quickly. After only 4 iterations, the root reached 1.13472 with a true error 0.00037%, which matched the actual solution. This slide compares the performance of the false position method and the Newton-Raphson method. From the graph, both methods converge to the same root 1.13472. However, the Newton-Raphson method converges much faster, reaching a true error 0.00037% in only 4 iterations, while the false position method requires 18 iterations. This is because the Newton-Raphson method uses the derivative to estimate a better approximation in each iteration, whereas the false position method only uses function value and converges more gradually. In summary, the false position method is more robust because it always keeps the root within the interval, while the Newton-Raphson method is much more efficient when a suitable initial guess and derivative are available. Therefore, for this problem, the Newton-Raphson method is the better choice because it achieves the same accuracy with significantly fewer iterations. This concludes part 1 of the presentation. Next, I will move on to part 2, which focuses on the statistical analysis. The objective of this section is to determine whether examination results from 3 different professors can be combined into a common grading scheme, and if not, to recommend a fairer grading approach based on statistical evidence. Before analyzing the examination results, several assumptions were established to ensure that the comparison among the 3 sections would be meaningful. First, it was assumed that all students complete the same examination paper under the same assessment conditions. This means they answer the same questions, follow the same marking criteria, and were assessed based on the same learning outcomes. Therefore, no section was considered to have taken an easier or more difficult examination. Second, any difference in the final marks were assumed to be caused either by difference in student performance or difference in marking practice of Professor A, B, and C. Since the examination scores alone cannot distinguish between these two factors, statistical analysis is required to determine whether the observed differences are significant. Based on the assumption, I will first examine the described statistic and frequency distribution of the 3 sections. This fixed grading scheme serves as the baseline and will be evaluated using the statistical analysis in tasks 1 to 3. From the summary statistic, Professor B recorded the highest average mark of approximately 69.13, followed by Professor A with 65.93, while Professor C obtained the lowest average mark of 55.07. However, the standard deviation ranged from approximately 9.3 to 10.9, indicating that the variability of marks is quite similar across the 3 sections. Next, I group the examination marks into grade intervals to observe the distribution patterns. Using the original fixed grading range, Professor A showed a relative balanced distribution. Professor B has many students concentrated in the B plus grade, indicating generally higher marks. In contrast, Professor C has more students in the middle and lower grade categories, suggesting lower overall performance. From these initial observations, we can already see that the 3 sections do not have the same performance pattern. Therefore, apply a single fixed grading range may not provide a fair assessment for all students. This slide presents the line graph together with the result of the Shapiro-Wilk normality test. Looking at the line graph, Professor A's distribution forms a very symmetrical bell-shaped curve. This is consistent with a normal distribution. Professor B showed a negative scale distribution, meaning that many students obtained relatively high marks, resulting in the peak shifting toward the higher score range. Professor C also followed an approximately normal distribution, but its peak occurs at lower marks because the class average is lower. To verify this observation statistically, the Shapiro-Wilk test was performed. The new hypothesis that the examination marks follow a normal distribution. For Professor A, the p-value is greater than 0.05, so we fail to reject the null hypothesis. Therefore, the mark can be considered normal distributed. Professor C produced a similar result with a p-value greater than 0.05, indicating its marks also follow a normal distribution. However, Professor B obtained a very small p-value, which is marks less than 0.05. Therefore, we reject the null hypothesis and conclude that Professor B's marks are not normally distributed. Overall, only Professor B violated the normality assumption due to the large concentration of higher scores. Follow the fixed grading range. The average grade for Professor A and B is B minus, while the Professor C is C. Since the three professors have different average marks, comparing students using raw scores alone would not be fair. To overcome this issue, the examination mark was standardized using Z-score. A Z-score measures how far a student's mark is from the section mean in terms of standard deviations. A positive Z-score indicates performance above the class average, while a negative Z-score indicates performance below the average. In this study, each mark interval was presented by its midpoint and the corresponding z-score and cumulative probabilities were calculated. The results show that the same raw mark correspond to different percentile rankings in different sections. For example, a mark that is considered average in one class may actually represent above average performance in another class. Therefore, converting mark in z-score providing a common statistical scale for comparing students from different sections more fairly. After then standardizing the data, hypothesis testing was performed to determine whether the three sections reasonably share the same grading scheme. First, a one-way ANOVA was conducted to compare the average marks among the three professors. The new hypothesis said that all three sections have the same population mean. The ANOVA result produced a p-value of 3.16 times 10 to the power of negative 21, which is far below the significant level of 0.10. Therefore, the null hypothesis is rejected. This means that there is strong statistical evidence that the average marks differ significantly among the three sections. Next, Revin's test was used to compare the variability of marks. In this case, the p-value is 0.524, which is greater than 0.10. Therefore, we fail to reject the null hypothesis. This indicates that although the average marks are significantly different, the spread of marks is statistically similar across the three sections. These two findings are very important. Since the means are different but the variability is similar, using the same fixed raw mark boundaries would not be fair. Instead, a grading scheme based on a standardized score is more appropriate because it accounts for differences in average performance while maintaining a consistent grading standard. Based on the ANOVA and Revin test result, I conclude that although the three sections have different average marks, their score distributes have similar variability. Therefore, instead of using single fixed grade B range for all students, I adjust the grading scheme so that grade B represents the average performance within each individual section. To achieve this, I first standardize all marks into Z-score, while the section mean correspond to z equals 0. Since the assignment did not specify the weight of grade B, I assume the grade B covers the interval from negative 0.5 to positive 0.5. This range represents students whose performance is within approximately half a standard deviation of the class average. Using the equation S equal mean plus z times standard deviation, the z-score boundaries will convert back into raw mark for each professor. Assume in the table, the adjust grade range become Professor A 61 to 71, Professor B 64 to 75, Professor C 50 to 60. These ranges are different because each professor class has a different average mark. This adjustment ensures that students with similar relative performance receive the same grade, even if their raw marks are different. Finally, based on all the statistical results, I recommend using a variable grading range instead of a fixed grading range. A, fit, a fixed grading range applies the same raw mark boundaries to every section. However, the ANOVA results show that the three sections have significantly different average marks. Therefore, using the same raw mark boundaries could unfairly benefit students from higher scoring sections while disadvantaging those from lower scoring sections. In contrast, the variable grading range adjusts the raw mark boundaries according to each section's mean while maintaining the same Z-score grading intervals. Since driving tests saw that the variability is similar across the three sections, this approach provides a consistent statistical standard. Overall, the variable grading range is a fairer grading scheme because it considers differences in section means, evaluates students based on relative performance, and reduces the effect of differences in marking standards. Therefore, I recommend adopting the variable grading range for all three sections. After determining the grade B range, I developed a complete grading scheme based on Z-score interval. Instead of assigning grade directly using raw marks, every grade corresponding to a specific Z-score range. For example, students with Z greater than or equal to 2 receive grade A. 1.5 to 2 correspond to grade A minus, 0 to 0.5 to 1.5 correspond to grade B minus plus, the, while negative 0.5 to positive 0.5 represent to grade B. The same Z-score interval are then converted into raw mark range separately for each professor using their own mean and standard deviation. Although the numerical marks boundary are different, the statistical meaning of each grade remains the same. The graph on the right shows the grade distribution after applying the proposed grading scheme. We can see that the distribution becomes much more similar across all three sections, with more students receive B plus or B and fewer students appearing in the higher or lower grade categories. This indicates that the proposed grading scheme provides a more balanced and consistent assessment across all three sections while maintaining a common grading standard. Finally, I evaluate whether the proposed variable grading scheme is fair for all three sections. The main strength of this approach is that it grades students based on their relative performance within their own section rather than using the same raw mark boundaries. It also accounts for differences in section means while maintaining a common statistical standard using the same Z-score interval. As a result, it helps reduce bias caused by differences in marking standard among the professors. However, there are some limitations. Professor B are not normally distributed, so the Z-score boundaries are only an approximation for that section. In addition, this method assumes that the differences in average marks are mainly due to marking standard rather than differences in student ability. Some students may also find relative grading less intuitive than a fixed grading system. Overall, despite these limitations, the variable grading scheme is still the fairest approach for this datasheet because it provides a more consistent and equitable basis for grading across all three sections. Thank you for your attention. I will be happy to answer any questions.